Hello everyone, welcome to Balance AI and the Deep Learning Foundation series. In this video, we're going to learn one of the most important ideas in deep learning and computer vision, and that's CNNs or Convolutional Neural Networks. Let me start with a simple question. How does an AI look at an image and actually recognize what is in it? Not just memorize pixels, but understand usual patterns like edges, corners, shapes, and eventually the whole objects. We can use something called dense neural networks, like the simple two-layer networks we have seen in the previous intuition videos. They work, but with dense layers, the connections explode too many parameters and they quickly become inefficient and miss something fundamental, especially when classifying images. That's where CNNs come in. In this video, I will explain what CNNs are, why they were such a big breakthrough for computer vision, and how they differ from the dense neural networks. This video is again part of my Deep Learning Foundation series. I have linked the full playlist in the description below. If you are new to my channel, and if you are new to the fundamentals of deep learning, I would strongly recommend you to watch these earlier intuition videos in this playlist, or to first understand how a deep learning model works in the first place, again, if you're completely new. If not, let's jump in and see how CNNs actually work. So what are convolutional neural networks? Well, they are networks that contain particular types of layers called convolutional layers. Before we understand what convolutional layers are, let's try to first contrast them with the dense layers. So we start with a simple 2D input image. Again, let's just take a grayscale image. Okay. So we take this grayscale image, and if we're using the dense layer as a hidden layer in our output, in our network, so we have to flatten this. So we flatten the 2D input pixels into a 1D vector. On top of this, we're going to add a dense layer. So because this would be the intermediate layer, we call this hidden layer, right? And on top of this, we're going to add the final layer, which would be our output layer, YPRED, right? And this is also a dense layer, right? So this is what we saw before when we built a neural network with just one hidden layer right here, and then one final output layer, right? And then we guess the weights, right? You guess the weights, which you multiply with the flattened input pixels, and you get the output in the hidden layer, right? You guess the weights again, right? And you compute the final, the unit in the final output layer from the hidden layer. That's what we've been doing. And once you calculate the loss, you take the gradients, you iterate over the process, you update the weights, and you continue the process. We've already seen this before in the previous videos, right? And then as we do this, this simple network becomes smarter, and it can predict what class this particular image belongs to. So in this case, this was a pullover, which was out of one of the 10 different classes. Again, just I'm referring back to this fashionist data set. In one of the previous videos, we have seen, how you build a deep learning model to classify these different images belonging to these 10 classes. So again, there, and as you can see here, this was based on simple one hidden layer in the middle, and then one final layer, and both these are dense layers. Okay, so what are these dense layers? The dense means here each unit in the layer is connected to every unit in the previous layer, right? Something like this. So I'm showing the arrows connecting only one unit here in the hidden layer, but imagine similar arrows from all the units in the previous layer, the input layer, connecting to the second unit in the hidden layer, and so on. So every unit in a layer is connected to all the units in the previous layers. Okay? These are the definitions of dense layers. So again, the hidden layer is a dense layer, the final output layer is a dense layer. Awesome. Okay, so this is a simple dense layer, simple neural network with one hidden layer, one final output layer. So what is the problem? Why do we even need convolutional layers? Well, apparently, there are some limitations here. Okay, some limitations of dense layers. Let's look at that. What are the limitations? Well, first of all, for the dense layer, right, you expect the input to be flattened. Okay, it's not, that's just one of the limitations, right? So you need to flatten this input, right? You can't directly use a 2D input, for the hidden layer. You first flatten it, and then you apply a dense layer on top of it. Okay, but most importantly, there's no spatial hierarchical structure of the image. There is no hierarchical patterns that unlearn. What it means is these dense layers or learning more or less the global patterns by looking at the entire image. I mean, it makes sense, right? I mean, you took a 2D image with all the pixels and just you flattened it. So you're kind of losing that spatial hierarchy there, right? So in essence, what's happening is you're learning the global patterns. So it's good, but there are some limitations. We can do better. And that's where the convolutional layer comes. So let's look at the same image and see what would we do differently if we use a convolutional layer. Okay, so the concept of convolutional layer is very interesting. It's just kind of almost all the way, like let's say human being is trying to classify an image, right? How do we look? We just don't like divide the 2D image into all like 1D pixels, and that's what we don't do that, right? We look at the different portions of the image with our eyes. We look at the different portions of the image and we try to recognize maybe some local features, some high level features. And once we learn a feature, in an image, we kind of remember it wherever that image might be coming. That's what a human would do. It's kind of similar to what a convolutional layer does. So what the convolutional layer does is it uses something called these windows. These windows, the blue things which you see here on the screen, right? These windows, they're also called kernels. They're also called filters. So if you see kernel, window, filter, they mean the same. So what this windows is doing is each window, let's just take one window here. Each of this window scrolls over this entire image. Starting from one portion, it just scrolls over the entire image. And as it's scrolling over, it's looking for different kinds of patterns. Right? Similarly, the second filter. So second filter is looking for some other different kinds of patterns. The third filter is looking for some other kind of different patterns. So the first window, as it maps this input image, it creates a new output image. Similarly, the new output 2D image. So the second filter creates another 2D output image. Third filter is looking at these things, and whatever it recognizes, it looks at some patterns, it creates a third output image. Right? So think of it, if it helps, think of it like a magnifying glass. Like maybe you're giving a magnifying glass, you take the magnifying glass and you scroll that magnifying glass over the entire image, and maybe you found some pretty interesting patterns and you put them in somewhere. Then you took another filter, another magnifying glass, and you looked at the image again. So this magnifying glass or this filter is looking at some slightly different patterns. Then maybe the third filter. Right? And then you collect all the things your filters or your magnifying glass has seen, and you put together and you create a final output shape. Okay. So this is, if it looks like a lot of theory, again, let me explain it further. So again, each of this window is looking for some kind of a local pattern. Okay. So so this is what the convolutional layer does. So let's take the three filters. Each filter scrolls over the entire image. When I say scrolls over the entire image, it's basically doing something called a convolutional operation. So each filter does a convolutional operation over the entire image. Basically, it scrolls through it and tries to come up with some interesting patterns. Okay, and in the process, it creates a new output shape, let's say. So this output image, which I just showed here, let's say this was identified or observed by the first filter, first window. Okay. Similarly, the second window here, that's going to get you, it's going to, once you do the convolutional one, it's going to scroll over the entire image. It's going to capture some other patterns, some other local patterns in the entire image, and it creates a new 2D output shape. And the third filter is going to capture some other local patterns, and it's going to create a third output shape. Okay. Now the final, each of these filter created a 2D shape, right? When you combine them, it becomes the final output will be a 3D shape, where the depth or each 2D surface in this overall 3D image, right, is basically the filter is capturing different types of local patterns, right? Awesome. So that's what this convolutional layer 1, conv 2D, you see what you see here, conv 2D 1, it's the first convolutional layer, right? It found some different types of local patterns. Okay, so then we're going to apply, let's say, another convolutional layer. On this, see now the original 2D input image has been transformed into a 3D input image, where each surface in the 3D input is containing different kinds of pattern in the original 2D input image. Okay. So you take this 3D input image, right, the output of the first convolutional layer, you apply another convolutional operation. What does that mean? You apply 3 more filters, let's say. Again, each filter, there is some slight change here, because now your output after the first convolutional operation is a 3D output, right? So your filters are also actually 3D. But for the simplicity's sake, here I just showed them as 2D. I'm going to explain that later. But each filter, imagine each filter is again going over this 3D output shape, right? 3D output shape, and it's again extracting some new patterns, okay? Some new patterns. Bottom line, you're going to get a new 3D shape, new 3D final output shape, okay? Hopefully this helps. So I'm going to clarify here. So once you have the, the input to a filter is a 3D, your filter is also a 3D filter, not a 2D filter. But bottom line, what I'm trying to tell you is each filter, right, in a layer is trying to capture different types of pattern. And each layer is trying to capture different hierarchical features or hierarchical patterns in the original input image. So the initial layers, right, they capture some local features. The subsequent layers, like for example, second convolutional layer captures even higher patterns, higher level patterns. Okay. Bottom line, see what we're doing is whether it's dense layer or convolutional layer, what are they trying to do? See, for example, dense layer, right? You want to transform the input data into more meaningful representation, right? Which is going to help you in classifying this image as as a pullover. But problem with dense layer is it's going to look at only the global patterns, right? Because you flatten the input pretty much. It's just going to look at the global pattern. Whereas convolutional layers, as you can see here, it's taking the simple 2D image. The first layer is converted the 2D image into a 3D input image, and it's kind of extracting all kinds of local features. And on top of that, you apply another convolutional layer. What that is doing is, again, it's trying to capture even more higher level features, right? Now, once, let's say we have two. So for example, in this, for our sake of understanding this convolutional layer concept, let's say we use only 2 layers, right? Then on top of this, what we do, finally, we have to flatten this. Okay, so we flatten this, the output from the convolutional 2D 2 layer, right? The second convolutional layer output, we flatten that. Then on top of that, we add the final output layer. Okay, well, the final output layer, and it's the same process now. So now you may ask, why did we flatten it again, right? Well, our final layer, the final output layer, the bipred, this is still a dense layer, and the dense layer expects the input to be flattened. So you have to flatten the output of the the second convolutional layer, whatever the 3D output you're getting, you need to flatten that. And then on top of that, you have your final output layer, which is also a dense layer, right? And then it's the same process. The difference between the dense layer is now with convolutional layers, you're learning local patterns. Patterns that are translational invariant. Again, it's a big English word. What it means is once the network learns a local pattern, it can easily recognize it even if the same pattern appears some other place. So it can learn patterns that are, it doesn't matter where they are appearing. The convolutional network can learn them. And then it also learns hierarchies of spatial patterns. So what are hierarchies? Hierarchy simply means, like, for example, layer 1 is learning, let's say, some finer, some localized, features. Whereas layer 2 is learning some aggregated features, more higher level features. So as more and more layers, subsequent downstream layers, if you add like hundreds of layers, right, the lower layers are learning some localized features, the higher level, the later layers, the downstream layers are learning more hierarchical features. Okay, so that's the beauty of convolutional layers. So if this concept of hierarchy of spatial patterns is still not clear, so let me, in the next slide, I'm going to explain that. But hopefully this slide here clarifies to you what's the main difference between, the dense layer and the convolutional 2D layers. Convolutional layers also transform the input data into more meaningful representation, except that it does it automatically, or almost all as a human would do, taking like a magnifying glass, looking at the original image and trying to capture or identify different subtle or finer patterns. And each layer is going to capture different, varying levels of these patterns. Okay. Now, in the next slide, I'm going to explain what this hierarchy of spatial patterns mean. Very simple example here. Again, this is from the book of Francois Collet of Deep Learning with Python. Again, it's an excellent book. He's the Francois Collet is the author of Keras. Okay, so and Frank Hoy in that book, he shows this image, which is, I thought, very, very cool. So you take the input image, right? Let's say it's a cat. Okay, I'm not showing the pixels and all that, just showing you the actual image, the 2D image. Okay, so now imagine you have two layers, and convolutional layer 1, as you can see here, what is this learning? It's learning all kinds of very fine low level features, like let's say the curves, the edges, right? All kinds of subtle, finer, localized features is what are being learned by the convolutional layer 1. Whereas convolutional layer 2, the second layer, it learns higher level features, more aggregated features. Like maybe now the layer 2 is recognizing eyes. Maybe it's recognizing the mouth and ears and the whiskers. So it's learning a little bit more higher features. And then finally, you have the final output layer, looking at this earlier local, lower level features of layer 1 and, the higher level features of the layer 2. Eventually, the final layer, it's going to be able to predict that, hey, this looks like cat. So the convolutional layers are just making it that much more easy for the network, right, to identify that this image belongs to cat. So hopefully this explanation help you, in understanding why convolutional layers are so amazing and so wonderful. In fact, they're like, pretty much they revolutionize the field of deep learning. See, nowadays we're hearing ChatGPT, LLMs, all of that, right? Which is awesome, because ChatGPT indeed in a way, brought general AGI, artificial generalized kind of feeling to the mainstream. But before that, the real breakthroughs in deep learning happened with computer vision. And that was again through convolutional neural networks. So that's the core intuition behind convolutional neural networks. We saw CNNs take a very different approach compared to dense networks, right? Learning from local patterns to hierarchical patterns and building up more meaningful representations layer by layer. In the next video, we'll go even deeper and look at how CNNs actually work internally. The all-important convolutional operation, or the convolution operation. This video is again part of my Deep Learning Foundation series. If you'd like to follow the full sequence, I have linked the playlist in the description. Please check it out. And if you're one of those who want a more structured, end-to-end path with all the hands-on projects, this lesson also comes from my Deep Learning Mastery course on Udemy. The link I have provided below. Again, thank you so much for watching. Happy learning, and we'll see you in the next video.